So let me continue with general complex exponential signals. If both C and A are complex, then in that case, I have a general complex exponential signal. In that case, I can write x of t as c times e to the power at, and this is equal to norm of c e to the power j theta times e to the power alpha plus j omega 0 t, and this is equal to norm of c e to the power alpha t e to the power j omega 0 t plus theta. So actually this is the general complex exponential. If alpha is equal to 0, then it means that both real and imaginary parts are sinusoidal. If alpha is larger than 0, it means that both real and imaginary parts are, of course, growing exponentially. Then if alpha is smaller than 0, it means that we have just the opposite, and both real and imaginary parts are decaying exponentially. As an example, let's assume x of t is 2 times e to the power 2 plus j omega 0 t, then it is equal to 2 times e to the power 2t, e to the power j omega 0 t, and it's equal to 2 times e to the power 2t cosine omega 0 t plus j sine omega 0 t. Of course, due to this alpha, this part is growing exponentially. So both real and imaginary parts are growing exponentially in this case. So if I just plot the real part, then it is a cosine and the amplitude is increasing. Okay, this is my real part. Well, the next example is just the opposite. I have 2 to the power minus t cosine omega 0 t plus j sine omega 0 t, and in that case, this part is decaying exponentially. Okay, well, what about discrete time complex exponentials? Again, you can write a discrete time complex exponential as x of n equals c times alpha to the power n, or in other words, x of n is equal to c times e to the power beta n, and if alpha is equal to e to the power beta, then we have both representations equal. In general, of course, alpha and c are complex numbers. Well, if we talk about real exponentials, then in this case, we have c and a are both real, and in this case, x of n is a real signal. Again, depending on the sign and amplitude of alpha, I have different cases. Let's assume that alpha is larger than 1. In that case, I have the amplitudes of n, amplitude of x of n is increasing. Well, if alpha is in the interval 0 to 1, then x of n is decaying as I increase n. Okay. Well, if alpha is smaller than minus 1, in that case, x of n is increasing in magnitude, but the sign is alternating. And finally, if alpha is in the interval minus 1 to 0, then I have a decaying signal in amplitude, and again, the sign is reversed. Well, if beta is purely imaginary, then it means that I have a sinusoidal x of n. So both real and imaginary parts are sinusoidal. So if I write real of x of n, then it is equal to real part of norm of c e to the power j theta, e to the power j omega 0 n. It's equal to norm of c cosine omega 0 n plus theta. So I have a cosine for the real part, or in general, a sinusoidal signal for the real part. And what about the imaginary x of n? It's equal to norm of c sine omega 0 n plus theta. So this is the imaginary part of my x of n. So in general, if beta is equal to alpha plus j omega, then I have damped sinusoidals which are decaying or growing, and they are the general form. And please check the book for the details. So next idea that we will discuss is periodicity of those discrete time complex exponential signals. Well, I remember in continuous time, let's say I have x of t, which is e to the power j omega 0 t. It is periodic for any value of omega 0. So regardless of omega 0 values, it's periodic. And remember, we have defined t0, which is 2 pi over omega 0, as the fundamental period. If omega 0 is larger in magnitude, then I have a higher rate of oscillation. So the frequency is higher. Well, in discrete case, the thing is more tricky because what we require is this. N is smaller n is of course an integer, and we require capital N, the period, to be integer as well. So x of n, which is e to the power j omega 0 n, is periodic only if omega 0 can be written in the form 2 pi times m over n, and both m and n are integers. And remember, n must be, let's say, it must be positive, so it cannot be 0 or negative. So if I have e to the power j omega 0 n, if it is periodic with capital N, remember, if it is periodic with capital N, then it must be equal to omega 0 times n plus capital N. And if you equate both sides, it means that e to the power j omega 0 n must be equal to 1. So if both are equal, then e to the power j omega 0 n be equal to 1. So what does this imply? It implies that omega 0 n is equal to somehow 2 pi times m. Because remember, what is this? E to the power j omega 0 n cosine omega 0 n plus j sine omega 0 n. If this is equal to 1, it means that the imaginary part is 0 and the real part is nothing but 1. If this is 1, then omega 0 n must be 2 pi m, because I know that cosine 2 pi m is 1. So this tells me that omega 0 must be somehow written in the form of 2 pi times m over capital N. So if you can write omega 0 frequency as in this form, then if both m and n are integer and n, remember, must be small, more than 0, then if it is the case, you can say that capital N is your period. So as an example, let's consider if omega 0 is 2. If omega 0 is 2, I can write this as 2 pi times 1 over pi. But of course, in this case, this is not in the form of m over n. So I cannot not write 1 over pi as m over n division. So I can say that for omega 0 equals to 2, the signal is not periodic. What about, let's say, omega 0 is equal to 6 pi over 41? Well, if this is the case, I can write it as 2 pi times 3 over 41. Then in that case, my n0 fundamental period is nothing but 41. So the critical thing is, if you have h to the power j omega 0 n, then it requires that you must write omega 0 as 2 pi times m over n. So this is periodic, but this is not. Remember, in discrete case, if you increase frequency omega 0, then it implies that your rate of oscillation is increasing. But in discrete case, this is not the case. In discrete case, if you increase omega 0 n, it means that rate of oscillation increases up to some extent. So what's the meaning of this? So let's write x1. Let's assume that I have x1 of n, which is e to the power j omega 0 n. Well, this is equal to, of course, this x2 of n for k being an integer. So what is this? x1 of n is e to the power j omega 0 n, and I tell you that this is equal to e to the power j omega 0 plus 2 pi k n. So what is it? This is written as, so this x2 is written as e to the power j omega 0 n times e to the power j 2 pi k n, and this is equal to cosine 2 pi k n plus j sine 2 pi k n. So if k is an integer, then what is this? This is, of course, 0, and this is, of course, 1. So what does it tell you? Both x1 of n and x2 of n are equal. So it means that x of n does not have a continual increasing rate of oscillation if you increase omega 0. Okay. So I have some examples here. Which of the following are periodic? For each, find the fundamental period if it is periodic. So I have x of t, which is e to the power j2t. Of course, t0 is trivial, 2 pi over 2. So it is equal to pi. So this is periodic with fundamental period of pi. Well, this is not periodic. Remember, I cannot write it as, remember, 2 pi m over n. This cannot be written. Omega 0 is simply 2, so I cannot write it as in this form. What about x of n equals e to the power j pi n? In this case, omega 0 is pi, and it is equal to 2 pi m over n. If m is equal to 1 and n is equal to 2, which is my fundamental period, or n0, I can say that this is periodic. If x of n is cosine pi n, then it is equal to real part of e to the power j pi n, right? So I can say that in this case, omega 0 is equal to pi, and n is equal to 2. So this is periodic. Well, these are some examples for x of n. So please review them as an exercise. Well, next section is 1.2. It is systems and basic system properties. We will first start with the definition of a system. A system is defined as any process in which input signals are transformed to output. So you have an input and you have the output. At the input, you have your signal, and at the output, you have the output signal. As an example, let's assume that you have an electrical circuit, and Vi is the input signal, and at the output, you have the out of T signal. So let me show you the case. Let's say this is an RLC circuit, and at the input I have an input signal, and at the output I have an output signal. So this is actually a system. So this is an RLC circuit, and this is a system with input and output relationships defined. Well, what is the notation for continuous time and discrete time systems? Well, x of t is the input, y of t is the output for a continuous time signal. For a discrete time signal, x of n is the input and y of n is the output. Well, we can also show them as in this form. X of t is input to a system, and I have y of t as the output. X of n is input to a system, and I have y of n at the output. Of course, this is for continuous time, and this is for discrete time system representation. Well, we have different interconnections of systems. For instance, I can have a series system. In this case, I have the inputs, and this is input to a system represented by, let's say, S1. Then the output of S1 is input to another system, S2, and I have the final output. Or if you have parallel systems, then in this case, I have S1 here, S2 here, they are parallel. I have the inputs, it is fed to both S1 and S2, and the outputs are sum, and I have the outputs. Well, I can have hybrid systems, which is composed of series and parallel, let's say, interconnections. Let's say I have S1 here, S2, and S3. So I have an input. It is inputs to both S1 and S2. Then the results of upper and lower branches are summed. Then this is input to S4. Well, I have here an input, an output, and there is a complex series and parallel systems in between. Also, I have feedback systems. Well, in those feedback systems, I have an input, and there is an S1, and there is an output. The output of S1 is fed to the input side with a feedback mechanism. So this is your feedback system. Systems has, regardless of their being continuous time or discrete time, systems have some properties. Well, the first property is memory property, and the formal definition is this: a system is memoryless or instantaneous if the output at any time instant depends only on the inputs at that same instant. So what is it? So let's say, assume that I have a memoryless system, which is y of t is equal to r times x of t. So this is, you know, IV relationship of resistor, right? So you have the voltage at the output, and you have the current at the input, and this is your resistance. So in order to find, let's say, y of 3, what do I need? It is r times x of 3, right? So in order to find y value for a specific instant, I only need the input at that time instant. So it means that it is a memoryless system. Well, as another example, let's assume I have y of t, which is equal to x of t minus 1. This is a pure delay system. So what does it do? It's simply, the input is simply delayed at the output. So in order to find, let's say, y3, what I need is x of 2, right? So it is nothing but a system with memory, right? So in order to find the current value, you need somehow the past value. Or this may be y of t can be x of t plus 1. It does not change. So again, in order to find y3, I need x of 4. So in order to find the current value, I need some previous or future values. So these are with memory. Another system with memory may be discrete time accumulator. So y of n is equal to summation k from minus infinity to n x of n. So this is an accumulator. And it sums, what does it do? It sums previous values of xn, right? So this system with memory, this accumulator, simply sums previous x of n values. Of course, this needs a memory to find y of n. Well, next property that we will cover is causality property. A system is defined to be causal if its output at any time instant depends only on the input at the same time instant or the past instance. Well, in memory property, to find the current value of the output, you need the current value of the input. If this is the case, you are memoryless. If you have a causal system, it means that you only need to find the output value at a specific instant. You only need the current value of the input or the values from the past. So you cannot have future values, only current values or the values from the past. So I have here a non-causal example. So what is it? Y of n is x of n minus x of n plus 1. So if I find a counterexample related with the definition, then I can say that it is causal or it is non-causal. So what is my counterexample? So assume I want to find y5. What is y5? x5 minus x6. So to find x of 5, to find y of 5, I need x of 6. So I need a value from the future. So a single counterexample is enough to show that this is non-causal. So this is in general the case. To find that a system is, let's say, having a memory, or if a system is non-causal, you only need a single counterexample. If you can find a counterexample, then you can say that the system is non-causal. Well, as a side note, of course, all memoryless systems are causal. Well, if you have a memoryless system, it means that to find the current output, you need the current input. So it is exactly within the definition of a causal system. So if you have a memoryless system, then it is a causal system. Well, I have more examples. Y of t is equal to y of t plus 1. Of course, this is non-causal. Again, I need a single counterexample. Let's say y0 needs, this is x. So y0 needs x of 1. So I need a value from the future. So I have a non-causal system. What else? y of n, let's say, is equal to x of n minus x of n minus 1. This is a causal system. In order to find the current value, I need the current value and one sample value from the past. What about y of t is, let's say, x of t minus 1. Again, this is a causal system. In order to find the current value, I need one past value. Well, next property is invertibility. A system is invertible if distinct inputs lead to distinct outputs. Well, clear? If a system is invertible, then a corresponding inverse system exists such that if I have x of n, and if S1 and S2, if they are in series, if again I have xn, so I have xn, it's input to S1, and the output of S1 is input to S2, then I have now x of n once more. So S1 and S2, when combined, actually they are not changing my signal. So in that case, S1 is inverse of S2, or in other words, S2 is inverse of S1. Or if in a continuous case, I have this one. So again, and then S1 and S2 are inverse of each other. So S1 is an invertible system such that S2 is the inverse. Well, as an example to invertible system, let's say I have y of t, which is equal to x of t minus 2. So, what is the inverse of this system? Let's assume that I define z of t, which is equal to y of t plus 2, and this is equal to, if I find y of t plus 2 here, so instead of t, you will simply put t plus 2. What is this? X of t plus 2 minus 2. This is equal to x of t. So y of t, this system defined by y of t is equal to x of t minus 2 is an invertible system, and the inverse system being defined by this relationship, z of t is equal to y of t plus 2, and when they are combined, I see that my signal is, the input signal is preserved at the output. Well, as an uninvertible system, or a system that cannot be inverted, I have such an example. Let's say y of n is equal to x of n squared. Well, this is an uninvertible system, and I will show this by an example. So let's assume that I have y of n is equal to 4. Then in that case, x of n is either plus 2 or minus 2, right? So this contradicts with this definition. So x plus 2 has corresponding output 4, and x minus 2 has again the same output of 4. So the system is non-invertible. So distinct inputs do not have outputs in that case. Well, this property is only for completeness, so please check the book for more details. Next property is stability. A system is stable if it produces bounded output signals for any bounded input signals. So you have a bounded input, and for bounded input, you have bounded outputs. So this must be satisfied for all bounded inputs if you have a stable system. Well, what's the definition of a bounded signal? Its value at any time is bounded by two finite values. So what is it? If I have a bounded signal, then let's say a is x of n is larger than a and smaller than b. In this case, I can say that x of n is bounded. or let's say x of t is in the interval c to d, then this tells me that x of t is bounded. Okay, so let's give an example to a stable system. Let's define y of n as summation k from minus m to plus m x of n minus k. Well, what does this system do? So it simply sums the samples of x of n. So it sums x of n plus m plus x of n plus m minus 1 up to x of n minus m. Okay, it sums the samples of x of n. So if x of n is somehow bounded, let's say by b, then what about y of n? Y of n is also bounded by b times 2m plus 1. Okay, so it's only small sign. So if x of n is bounded, then in that case y of n is also bounded. Okay, so bounded input leads bounded output at the output. Well, what about example to an unstable system? Y of n is, let's say, from minus infinity to n x of k. So what does it do? It sums the samples from minus infinity to n. So this is non-stable. So I will show that this system is unstable. I will show this by an example, by a counterexample. Assume that x of n is equal to u of n. Okay, so what is the sum? In that case, y of n is simply n plus 1 times x of n, right? It sums the samples from 0 to n because the negative values are 0. So as n goes to infinity, this y of n again goes to infinity. So this is it means that if all the input is bounded, output is unbounded. So this y of n is n plus 1, and for x of n, as n goes to infinity, y of n goes to infinity as well. So as another example, assume that I have y of t which is equal to x of t squared, and if again x of t is bounded by b, then y of t is bounded by b squared. So bounded input leads bounded output. Okay, this is the case. So as an example to unstable system, I have y of t, which is integral minus infinity to t x of tau d tau. This is an integrator. It integrates the inputs. Again, if my, let's say, x of t is, again, if it is u of t, so this is my x of t. This is u of t, which is u of t. So what does it do? It finds the area under this curve up to t, right? So this is my y of t. And as, of course, t goes to infinity, of course, y of t goes to infinity as well, although x of t is bounded. So x of t is bounded by 1, and as t goes to infinity, y of t goes to infinity as well. So I have an unstable system. Next property that we will discuss is time invariance. A system is time invariant if a time shift of input causes a time shift at the output by the same amount. So what does it imply? X of t, let's say y of t is the output for x of t, and let's say if x of n is the input, you have y of n. So if you shift the input by t0, it means that y of t must be shifted by the same amount for, of course, all t0 and t. Or if I have x of n minus n0, if input is shifted by n0, then output must also be shifted by the same amount, of course, for all n0 and n. So this is the formal definition. Now I have an example. Let's say y of t is sine of x of t. So x of t is the input and sine xt is the output. So let's assume I define my yt as sine of x1t. So in order to show time invariance, I will shift inputs. So I will shift x1 and find x2. So this is, let's say, x1 of t minus t0. So I somehow shift the inputs. So what does this mean? If I shift the input by t0, it means that, let's write y2, which is sine x2 of t. So what does this require? What does time invariance requires? If input is shifted by t0 and I have x2, then y2 must be the shifted version of y1 by the same amount. So this is equal to sine of x1 t minus t0. And I know that this is equal to y1 of t minus t0. So of course, this means that I have a time invariant system. Okay. So I shift the input by t0 amount, and at the output, the result is shifted by the same amount. So I have a time invariant signal here. As another example, let's say I have y of n, which is equal to n times x of n. So the procedure is the same. I define y1n, which is n times x1n. Then I define x2n, which is x1 of n minus n0. So I shift the inputs by n0 to find x2. Then I will find y2 of n, which is n times x2 of n. Simple, I'm just using this definition. So instead of x2 of n, now I'm putting x1 of n minus n0. So of course, this is not equal to y1 of n minus n0. What is y1 of n minus n0? It is n minus n0, right? x1 of n minus n0. So since those two are not equal, then I can say that the system is not time invariant. Okay, those two must be equal for time invariance. Well, as another example, let's say I have yt, which is defined as x of 2t. So I will show that this is not time invariant by a counterexample. Let's assume this is my x1t. It is from -1 to +1, it is 1. So if this is x1, what is y1? Y1 is simply sorry. So y1 is simply this signal from -1 to +1. So this is y1, okay? So x of 2t, let's write here. Let me shift x1t by 2 units in order to find x2 of t. So let me define x2 of t as this. It is the shifted version of x1t. So x2t is simply x1 of t minus 2. So I shift this signal 2 units right to find x2 of t. So what about y2 of t? So this equals to x2 of 2t, right? And it is this signal. So what is this? I have shifted input to the right. So I have shifted input to the right, yeah, by 2 units and obtained x2 of t. And by using the definition y2 of t is x2 of 2t, I obtained y2 of t. So is this for time invariance? Y2 of t must be equal to y1 of t minus 2. So I have shifted the input by 2 units, and the output must be shifted again by 2 units. But what if I shift y1t by 2 units? If I do this, then it is in the interval 1 to 3. So this is my y1 of t minus 2. Well, when I compare y1 of t minus 2, of course, this is not equal to y2 of t. So my system is not time invariant in that case. So this time scaling signal, I can conclude that this time scaling signal is not time invariant. Well, here you have your exercise. Let's y of n is defined as 2x of n plus 3, and check whether this is time invariant or not. This is your exercise. Well, the last property is linearity, and the formal definition is this: a linear system must satisfy the superposition property, which is as follows. So I have, if I have x1t and y1t is the corresponding output, then I have x2t and y2t is the corresponding output, then it must satisfy 2 properties. First, if I sum the inputs at the output, the corresponding responses must be summed. So this is called as additivity property. Additivity property. And the second property that a linear system must satisfy is the homogeneity property. If I scale the input by an amount, the output must be scaled by the same amount. So this is called as homogeneity property. So a linear system must satisfy both additivity and homogeneity properties. Well, or in short, so it means that I can combine those 2 properties. If I scale both inputs, if I scale both inputs, then at the output, I have the scaled and summed versions of the outputs. So I scale and sum the inputs. The output of the system to that input is scaled and summed versions of the input. So this is, of course, similar for discrete systems. As an example to a linear system, let's write y of t is equal to t times x of t. So first I define if x1t as at the input, let's define y1t as t x1t, and if x2t is at the input, let's define y2t as t times x2 of t. So let me define x3 of t, which is equal to a times x1 plus b times x2t. So if this is the input, so if x3t is at the input, I have y3t at the output, and it is equal to t times x3 of t, and it is equal to t times, if I write a x1t plus b x2t, then this is equal to a times t x1t plus b times t x2t. And this is nothing but a times y1t plus b times y2t. So this is a linear system. So if I scale and shift the inputs, outputs are also, if I scale and sum the inputs, outputs are also scaled and summed. This is an example to a linear system. Now my second example is a nonlinear system. So let's have y of t defined as x2 squared. So if x1t is at the input, then I have y1t at the output, which is x1 squared t. If again x2t is at the input, I have y2t at the output, which is x of t squared. If I define x3t as a times x1t plus b times x2t, then at the output I have y3t, which is equal to x3t squared, and it's equal to a x1t plus b x2t squared. And this is of course equal to a squared x1t squared plus 2ab x1t x2t plus b squared x2t squared. And of course, this is not equal to a times y1t plus b times y2t, which is equal to a x1t squared plus b x2t squared. So what does linearity require? Scale and sum the inputs, scale and sum the outputs. Okay, so we have shown that this is not satisfied. If I scale and sum the inputs for such a system, outputs are not scaled and summed. So this is not a linear system. Well, here I have an example for you. Please try at home that y of n is equal to 2x of n plus 3 is a non-linear system. Well, this is interesting that this system is a nonlinear system. Well, y is equal to x plus 3 is defining a line, but regardless of that, this is not a linear system. So please show that this is not a linear system. Also, this is your exercise. What does it tell you? It tells you that there's a system here, and this system is not memoryless, it is not causal, it's not stable, it's not linear, and it's not time invariant. So this system does not satisfy those memorylessness, causality, stability, and linearity. So the question asks you to drop a minimum number of terms from the right-hand side to make the system linear, stable, causal, time invariant, and memoryless. Well, by just looking at this, you can say that, well, I will not solve it, but what you can say is this. Actually, this term here, n times x n minus 1. So this violates memorylessness, right? This n times x of n minus 1 is having a memory. To find the current value of yn, I should need a sample from the past. Also, it violates time invariance property, so I must omit this. This violates linearity, I should omit this. What does this violate? This violates stability, so I must avoid this. So you should erase some terms such that at the output you have those properties, but remember, you should drop minimum number of terms from the right-hand side. So please try this at home by yourself. As another example, I ask you to determine the properties of the system y of n equals real part of x of n. So that's all for today's lecture. So we have seen the exponential signals, and we have seen some systems and their properties. So let me